Okay, we can get started. It said he won't be able to join today, but thanks for joining. We'll get going. One request I have for the lecture today is it kind of starts from the very basics and goes through the ideas of building a basic neural network, linear network to predict digits, and the concept of backpropagation, automatic differentiation. And all along, what Jeremy does is he builds the pieces of the logic or code that is needed to make the to implement backpropagation ourselves, if you will, in code, the pieces that make it realizable, and then switches to using the PyTorch versions. As he promised in the first lecture, he doesn't use anything in PyTorch that he hasn't built himself through part of the lessons. If a lot of this is a refresher or just basics for you, I apologize, but I think sometimes it helps to get back in touch with the foundations and then build it up from there. And some things get clearer each time. At least I go back and understand a little bit better. So with that, let's get started. I'll kind of switch between slides and the notebook periodically. So let me know if you're not seeing what I'm talking about by speaking up, because as I switch, I sometimes might miss. Can you folks see my slide?
Yeah, we can.
Okay, good. So we'll start with really basic fundamentals. And one of the things I really like about Jimmy's past courses is the fact that he demystifies a lot of what is often hidden in terms of deep learning behind terminology and jargon that tends to be a barrier to understanding, or at least appreciating that what's behind deep learning is not, it is math, it is linear algebra, but it's not so complex that with a little bit of additional curiosity and inquisitiveness that we can build that knowledge on our own. So we start off with basics of calculus. If we plot distance on the y-axis and time on the x-axis, and we assume that there is a car or vehicle of some kind moving along at a particular speed, then if we plot the distance y as a function of the time, then this line that you see going between the x and the y-axis could be a plot of such motion. And what we have seen in high school calculus and so on is the basic differentiation concept is that of rise divided by run, that is the rate of change of your distance with respect to time. So if you travel 10 meters in 2 seconds, then the rate of change, which is the speed, is 5 meters per second. So you can think of it as a function of t is the distance, then function of t2, which would be y2, subtract from that the function of t1, which is y1, and then subtract the two appropriate distances along the, time values along the x-axis, and you get the difference in distance traveled divided by the difference in time, and you get the rate of change, which in this case is 5 meters per second. So that's kind of a very basic touchback of what calculus is. It is, that's all fine and good, but that's, linear. What happens if we have a curve that's actually a plot of distance is no longer a simple straight line, but it's something of a curve like shown here. In that case, what we do is we try to calculate the speed at a particular point in time along this curve by finding the tangent to the curve at the point of interest and moving just a tiny amount, the tiniest of amounts possible, and calculating the change in distance and dividing it by the tiniest of changes in time. And what we can illustrate that by is saying a function of again, a time t1, but with a very small increment of time added to it. That's often shown as delta. Here he uses the term t. And subtract from that the original time we started at, which is t1. And we take the function which converts it, this time to a distance. So this is again the change in distance divided by, and if you subtract t1 plus t and t1, what you're left with is the difference. So a very tiny difference, which is infinitesimal. And therefore, we kind of again go back to the rise versus run concept. And in this case, we refer to it as dy by dx. His key point here is to illustrate that you could potentially think of this change as change of or infinitesimal change, a very, very tiny amount of change. And therefore, his point is that when we use what we'll later come to, which is the chain rule, that is, if in this particular graph, we have chosen y, which is distance, as a function of a single variable x. But if it weren't, if it were to be a function of some variable, say u, and then u were to be a function of some other variable x, then we are composing, then when we do that, we call that composition of functions. So y is a function of u is a function of x. And when we do that, what we end up with when we want to find out how does y change when we change x. So conceptually, we are getting to y from x through an intermediate function u. Then we arrive at what is called a chain rule, which we get into in little more detail in the subsequent slide. We figure out that what we have to do is to multiply the differentiation terms together. So we think of dy, the change in y, when we change x. So dy by dx is dy by du multiplied by du by dx. And there's arguments as to why you cannot view this as just elimination of du and so on, but we'll get into that later. The basic concept is that differentiation is small changes in function. And when we compose functions, then there are rules by which we figure out how to compute the derivative of a composite function. And how when we change x, which goes or reaches to y through a multitude of functions, how do we calculate the various components of the derivative? That is, how does y change when we change x? Now, obviously, this is all a single variable and in just 2 dimensions. So we're just viewing distance as a function of time. But it so happens that now when we begin to move towards what we want to discuss, which is how do we compute changes and how do we use a neural network to predict and to get our predictions to be better, then we're looking at more complicated concepts. So for example, let's say the curve that we are trying to emulate using a neural network, that is, we want the neural network to generate an output which is close to a particular function, and the function that we want to emulate is that shown here, which is an inverse parabola, if I remember my math terminology correctly. So what we start off with is, let's say we just have straight lines in order to emulate this particular graph. Then how do we proceed just using straight lines? So the first thing we can do is draw a straight line, such as what he has shown here. And we all know the equation for a straight line from high school. It's y equals to mx plus c. So that's what we have here. But that doesn't get us anywhere close to the curve which bends, if you will, in the right-hand portion of the curve. So let's say we want to be able to get closer to this curve. What do we do using just straight lines? Well, one of the things we could potentially consider is adding straight lines. So if we were to draw another straight line, and this straight line, for a minute, assume that the straight line that I'm pointing to here on the screen goes straight through all the way across. But by some means, we limit the straight line such that we don't calculate its values when it is above 0. So what we have done is chop off the line when it's above 0, and then we calculate it. We allow the line's values to exist when it's below 0. So if we do that, and for all points to the right of the leftmost blue circle that he has drawn, if we assume that the next line that we want is the combination of the first line we drew and the second line that we have drawn below, assuming that we have zeroed out any value of it above 0, then what we begin to see to the right of the blue line is it will be the combination of the values for this line and the values for the line going down below. So therefore, the net result, roughly speaking, would be this line. Now, as you can see, this particular line is a much better approximation to the curve than just a monotonically increasing single straight line. We could, given that the curve bends even more dramatically, given that the curve which is even more dramatically downwards, we could do the same thing a little bit to the right, and again use another line where we zero out this scratched out blue part, and again add this value to the value of now our new line that we have formed by the combination of these two lines initially. Then we'll find that the net result of that is a further reduction down. So conceptually, this is what we are doing in when we build linear neural networks. Unfortunately, I wish we had used actual parabola instead of reverse parabola. The reason for it is conceptually what he is using here is kind of an opposite of a ReLU function, because in a ReLU function, the actual function would look like the exact reverse of it. That is, we eliminate all values below 0, and then we add or allow to remain all values above 0. But it doesn't matter which. You could consider a very simple inverse ReLU function and add the linear function to an inverse ReLU function. The point being that what a basic linear function combined with some form of a ReLU, a linear network, which is just a combination of linear functions combined intermittently with the ReLU function, is essentially a composition of functions which enables us to emulate any given function that we want to emulate. Now, we have so far talked only about 2 dimensions because it's easier to visualize things in 2 dimensions, y and x. But in reality, when we look at and when we go to the actual neural networks, they exist in a vast multidimensional space. So that's what he attempts to convey here. So instead of thinking about what I've been mentioning as straight lines, you can think of them as planes. So in effect, if we are trying, and again, we can only visualize in 3 dimensions at most. So this is a 3-dimensional visualization that he has attempted on the right. But think, and as Glenn Hinton often says, the way to visualize a 10-dimension thing is to say 3 dimensions is to visualize in 3 and just say 10 dimensions. So think of this as potentially existing in 10 dimensions. The point is that you would be combining a tremendous number or a large number of planes which are linear, and intermittently combining the ReLU functions in order to emulate the desired plane or a desired outline of a plane that we're trying to emulate, which is the function that we want to get close to using the linear network. So that's a lot of kind of theoretical explanation of how we get to emulating a function that we want to emulate using linear networks and ReLU functions. So conceptually, that's what we are talking about. And now we switch to trying to build such a network. Can you folks see the notebook?
Yes, we can.
Okay, thanks. So what we have here is essentially it downloads the MNIST dataset from, I believe he does that from Hugging Face. But what the MNIST dataset is a set of images, each of size 28 by 28. In the training set, there are 50,000 such images, black and white, binary, if you will, values, or sorry, black and white values, I should say, not binary. 50,000 training, 10,000 valid, and 10,000 tests. We won't worry about tests, but we'll be working with, say, the 50,000 training examples and the 10,000 validation examples. So it just loads them into the appropriate X-train, Y-train. The X-train are the images. The Y-train are the labels for the images. So if you see an image and it's the image of a digit 3, the label will be 3. And since the images are of integers from 0 to 9, the total number of integers that we are trying to predict are 10. So that's kind of the basics of the MNIST digits. What we try to figure out first, and one of the things, as I've said many times before, is for yourself to play with, and as I've done in the notebook, add your own comments and stuff. So the understanding of the various functionality that exists in the notebook becomes clear to you, and you can go back and refer to it if in case of confusion later. What we do here is
increase the font size. Font size, please. Yeah, that's better.
Okay, so what we see here is just the shapes. So X-train, as I told you, is 50,000 values, and M would be the rows, and the rows are flattened from a 28 by 28 image. So 28 by 28 is multiplied is 784. So that's the reason when you do NM and then from an X-train dot shape, you get 50,000 and 784, N and M respectively. And then C, which is the number of classes that you are trying to predict using the neural network, is basically the count of the number of digits. So as I mentioned, it's between 0 and 9, and that makes it 10. So you say Y-train max, and Y-train is between 0 and 9. So the max value is 9, and you add 1 to it, 10. So there are 10 digits or 10 classes that you're trying to predict. So 50,000 values of 784 pixel values, and the prediction classes that you have are 10. So that's what you determine by this cell. We are building a basic neural network using 2-layer networks. So the first layer goes from the 50,000 input to 784, 50,000 by 784 to 50,000 by 50. So we have a number of hidden neurons is 50, and then from 50, at least initially, for simplification of the concepts, he just uses, let's just assume we predict a single digit instead of something that we'll look at later, which is predicting the probability of the image being any one of 10 digits. For simplification, let's just first assume that our network, all it does is it produces a single prediction of what it believes to this particular image to be an image of which digit. Okay, so the output initially we will think of is the network that we'll use produces an output of a single value, a single scalar value. So this is the number of hidden. Now we initialize what are called weights and biases, which are the elements or parameters, as they are called, or the values that we have for each of the linear networks in the neural network that you are building. So we have two layers. As I said, there's a single hidden layer. The input goes into the first layer, which has a weight and a bias of W1 and B1. And that the output of that layer then goes into the second layer, which has an input of W2 and B2. And in between the first and the second linear layer, we insert what is called a ReLU function, which we'll see in a minute. We initialize the shapes, and why these shapes are the way they are is something that you should kind of work out for yourself. The first layer will have 50,000 by 50, if you will, the weights. The bias will be similar to what the output value will be for the first layer, so it will be NH. The weights would be NH leading to 1. As I mentioned, the particular neural network we are looking at currently is one that produces a single value. And again, we initialize the B2, which is the bias for the second linear layer, with the dot for zeros, which essentially initializes the biases to be zeros and the weights to be some random values. And the weights are matrices, as are the biases, but the shapes are as shown here. Okay, what is a linear unit? So a linear neural network unit is basically something where we multiply the incoming input. So in this case, recall that the first layer has 50,000 by 784, 50,000 rows of 784 columns, and we multiply it by a weight matrix. So in order to be able to multiply X and W together, as we saw in the tensor last lecture, W has to have a 784 by whatever value matrix, because the inside dimensions must match. That's the reason that you can see that W1 is M by NH. And you see that here X times W plus B is defined as a linear unit. So if we then use this definition that we have defined ourselves of a limb to be X matrix multiplied by W and add B, and we use X valid, remember that is 10,000 by 784, and we use W1 and B1, then, and these are the kinds of things that you should play with yourself, is given that this is 10,000 by 784, this will be 784 by 50, and this is 50. So what would be the multiplication? Work it out, and you would then see that the shape of T would be 10,000 by 50. So that's essentially what he's trying to show here. And the reason to work through such very simple and trivial examples is to get familiar with the matrix multiplication and what you expect the shapes of outputs to be, and then confirm it by running the notebook. But just mindlessly running the notebook otherwise doesn't teach you a whole lot. As I mentioned, the ReLU function is nothing but clamping. Kind of think of it as the reverse of what I had illustrated in the slides. It basically clamps all the values which are below 0 of a function. So it's simply stated as X. If X is greater than 0, then the value is allowed to pass through. And if it's less than 0, then the value is clamped at 0. So ReLU of X is X clamp minimum to be 0. So anything below 0, any negative values are clamped to 0. So if you take T, which is this 10,000 by 50, and if we just to illustrate, let's look at T here, and you'll see that there are negative values, right? 11.39, 11.25, 0.09. But after passing T through the ReLU unit, you'll see that the 0.09 has gone to 0, The 1139 is 0. The minus 14.49 is 0. So anything which is negative in t is clamped to 0. Now let's just build a model ourselves of a very simple neural network. So if we say that xb is the input given to a network, then we define L1 to be a linear function of xb with weights w1 and d1. L2 will be the output of passing L1 through a ReLU function. And then what we return is the linear output of L2, which is the output of the ReLU, passed through another linear layer with weights and biases is W2 and B2. That's what is our model definition at this time. So then if we pass our, and so far remember what we're passing is X valid. So if we pass X valid, which is 10,000 by 784 input to this network, and again, it would be important to work through. So we go 10,000, 784 multiplied by 784 by 50. So the output would be 10,000 by 50 at the output of L1. So L1 shape will be 10,000 by 50. ReLU doesn't change the shape. All it does is clamps the value. So again, L2 shape will be 10,000 by 50. When we pass that through the linear layer, which is the second layer, then 10,000 by 50 goes to 10,000 by 1. So what we have done through the linear network with ReLU in between is gone from a 10,000 input validation set with 10 digits each to 10,000 values of what the network believes is the prediction for each of the images, what the corresponding digit is. So that's what the result shape ought to be. And by working through it, we check that by running the actual code to the model or the model code, and we find that it's 10,000 by 1. Okay, so then switching back to the slides, for simplicity purposes, let's assume that the loss function, and we'll talk about the loss function as to the purpose of the loss function. But let's assume that what we are trying to do is we take the output from the neural network. So we take the single value that the neural network in this case produces, and we compare it to the Y value that we actually know the network, that the digit actually is, and we define a difference between the two. But before that, let's just work through what I have kind of talked about in the notebook. What we're building is a simple digit recognizer, right? A neural network with 2 layers. With a hidden junction of 50, a single output 2-layer neural network. And the loss is, we're assuming it's an MSE loss. And there is a reason why we do that. It's to keep our math simple. Eventually, we'll find out that a better loss definition is possible, and we use that loss. But here we are using MSE because mean square error is something, or a square error is something that we can compute very easily. So for purposes of explanation, it's easier to use the MSE loss initially. Now, this is just mathematically working through the equation. So L1, as I said, is the linear of input W1 and B1, which translates to the equation that we have seen: input matrix multiplied by W1 plus B1. The add sign is matrix multiplication, as we saw in the notebook. L2 is ReLU of 1, out is this. The loss is the MSE, and the MSE is, as I mentioned, the difference between the out values that the network produces. So the network produces, remember, single output, which it thinks is the value that it's trying to predict for the integers, whether it's the image is a 3 or a 5 or a 7. And we take the difference between that and the actual integer value that we know it is. So for example, if it predicts a 3 and we know that the actual value is a 5, then we take the difference between a 3 and a 5 and we square it and then take the mean. That's what mean square error. So first square and then take the mean. And the difference is the out dot squeeze. And we'll kind of look at the notebook to understand why this particular modification of the shape is needed in order to get the correct subtraction. And the target, as we well know, is the y, which is the integer value. Now, as I mentioned, and I've already kind of talked through this, so I won't repeat it, but it's important to work through the shapes as we go through a simple network, because these things become much more complicated as we go through more complex networks. But it's important to understand it with simple examples, because the concepts don't change even as the networks become more complicated and so on. So what he then tries to explain, as I mentioned, what we have gotten as output of the neural network, even though it doesn't illustrate here the two layers. Think of the left-hand side as having two layers with a ReLU in between. But what we eventually get is the single output. Let's assume that the output is a 9, and the actual value of the integer that we're getting is, or that we know the image is representative of, is 2. Then in this particular instance, we are going to take the mean square error between a 9 and a 2 and use that as our loss. Now, one of the concepts he doesn't get into in much detail here in the lecture, but he covers it in his first series of courses quite a bit, is the key concept. I'll spend a minute on it. What we are actually interested in the output and the performance of the network is, in fact, the accuracy. As we'll see later, he defines the accuracy as a function. But we use the loss function in order to get our neural network to perform better over time as we train it with many examples. The reason for that is that the accuracy function, which is a function of how accurate is our output compared to what we expect, what output does it give, it's not a great function to use for the purposes of training the network, because the accuracy function doesn't have the ability to modulate the network, that if it's not differentiable with respect to the inputs. So what often is done is we use a proxy function, which is called the loss function, which is used in order to determine how to change a lot of the variables that make up the neural network in order to make the neural network behave better in its ability to predict the desired output that we have. So what is often called, or what is invariably always called, the loss function, you should always think of it as a proxy function for getting to the goal that we want, what we want the neural network to be able to predict. But the reason that the loss function is often different from the goal that we are, sometimes it is the same as the goal, but the reason to use a loss function, or the loss function chosen, is because the loss function is a differentiable function of the inputs and the variables that are used in the network that then generate the output of the network. Okay, so that's the reason here that we don't directly use accuracy as a loss function. We instead use mean square error, and then subsequently we'll see we use another proxy function called the cross entropy. And those functions are better because they allow us to use the back propagation. Basically, they allow us to use the, they are differentiable with respect to the variables of the neural network. And therefore, when I say differentiable, what again does it translates to is we can wiggle these functions, much like we were wiggling the, when the basics of calculus, we saw that we wiggle the distance with respect to time. We can figure out how much does a change in time give us a change, or vice versa, how much does the distance change when we change the time. In this case, how much does the prediction of this number 9 change and get closer to what we actually want, which is the number 2, when we fiddle or move these pixels of the images even a little bit. So that's kind of what we're after. And the concept of a loss function is a proxy function for what we actually want in order to get, and the hats are typically predicted values, and the no hats of the labels, that is y and y hat. Y hat is typically predicted value and y is the actual value. So in this case, what we're trying to do is to say how close, using MSE as a function, is the predicted value to this. Now, I'll also cover another important thing which he doesn't touch on. He does mention there is a reason why the MSE value, why MSE is not a good loss function for this particular network. Can anybody talk to or comment on why they think it's not a good loss function? I already mentioned why it is a good loss function, in the sense that it is differentiable with respect to the input. So in that sense, it's definitely a good loss function, but it's still a poor loss function compared to other loss functions we can use. And there's a reason for that. Can somebody comment on that or have any thoughts?
Is it like
Why the MSE
compute?
function?
Like like you have to take the square, or is that? I don't know. I don't know. I'm just thinking aloud.
Yeah, it is related somewhat, but indirectly to what you said, Mehul. The reason it's a poor loss function is, in this case, remember, we are just predicting one value, right? So we're just predicting, say, some digit. And in this case, we just assume that it's a 9 and a 2. The reason it's a poor loss function is, if this value that it predicts is 9 compared to a 2, the mean square error between a 9 and a 2 would be much larger than between a 5 and a 2. That is not actually indicative of anything, even though the loss function seems to indicate that it's important. Do you follow what I'm saying? That is, if it predicts a 9, the mean square distance or the mean square error between a 9 and a 2 is much larger than between a 5 and a 2. But it's meaningless from the point of view of our network trying to predict an accurate value.
Oh,
because the network, all we wanted to do is to detect the pixels and how they change. So if actually the pixels have to be fiddled, so it's a 5 and a 2, then versus a 9 and a 2, there's no meaning to 9 being farther away from a 2, which is a numerical concept, coming into the picture, or coming into the equation of y images that it's trying to predict. So that's the reason why MSE is not a good loss function in this case, right? Because it says that if the network predicts a 9, oh, I'm far away from a 2, but that's not really true. You could conceivably have 5, and that could be far away from a 2 too. There's no good reason why, just because the number 9 is far away from a 2, your network somehow should be penalized for that. Your network should be penalized if it's unable to recognize the bits arranged in the form of a 9 or a 2. Does that make sense? So that's actually the reason why an MSE is not a good loss function, even though it's a good loss function from the point of view of differentiable inputs.
Okay.
Right? So that's where, the choice of loss functions, as we'll see much later in the course, becomes an important contributor to how well a network trains to be able to predict. Okay, so now we begin to, assuming that our output is from the network is a particular value, a single value, and we compare it to what we know to be the actual integer value. And we use the MSE as an indication of how far is the predicted output from our desired output. And now, how do we make our network that we have created? Remember, the network is 2 linear layers, a ReLU in between, and the MSE function is something that we have stuck at the output. What we are now saying is we start off with a random set of values for the weights and the biases that we have introduced for the linear layers in the network. The question is, how are we going to tweak the input values and the weights and biases? Actually, we don't tweak the input values, sorry, we tweak the weights and biases that we have, which is the W1 and the B1 and the W2 and the B2, right? How do we tweak those values so that our network gets better at predicting the desired output? That's the question or the problem that we're trying to solve. We start off with a random set of values as we saw for W1 and W2 and zeros for B1 and B2 in this case. And we want to fiddle the W1, W2, B1, B2 such that, when I say fiddle, move them by small, tiny amounts, such that our loss reduces, because we have a particular loss by starting off with random values. That loss, let's say, causes the value that is predicted, starting with random values for W1 and W2 and B1 and B2, our network outputs 9. But we know that the actual value is 2. So we calculate the loss. The question is, using this loss, how do we determine, or in what direction should we change W1, W2, B1, and B2 so that our loss gets smaller? Because the smaller the loss, the better is our ability from the neural network to predict the desired value, right? So much like this is where the concepts of differentiation, forward prediction, and backward prediction come into play, and the terminology of back propagation begins to be relevant. So what we are trying to do is, if we look at next slide, what we're trying to, let's think of each of the layers as kind of a box with certain inputs and certain outputs. So when we go forward through the network, we have input going in to layer 1, which is a linear layer. We have, ignore the .g and so on, but we have W1, and I've deliberately not indicated B1 here, but W1 and B1. We have the output. What will be the output here? That's L1 going into ReLU. What's the output of the ReLU? It's L2, as you can see here. Goes through another linear layer. There's a W2 here and a B2, which are values that are of the weights and the biases. And then output of the linear layer, which is the out, we call that out. You can see that here. And then out goes to the loss, which is the MSE of the out and the known Y integer value. Okay, so that's the network that we've built. Now, as I said, what we want is, okay, we have computed the loss. The question is, how do we reduce the loss by changing potentially the W1 and B1, W2 and B2, the L1, L2, and so on and so forth. Because when we change W1 and B1, the input remains the same, L1 will change. When because L1 changes, L2 changes. Because L2 changes, and if we change W2 and B2, then out will change. That's what we want. We want the changes such that the loss reduces. How do we do that? How do we distribute the change that we, or how do we make the loss go down? And when we have a reduced loss, how do we distribute that? That's when I say distribute, it means how do we kind of make the value of a change in loss and distribute it across the change in W, the change in B2, the change to the L2, the change in L1, leading to changes in W1, B1, and inputs. So what the method by which we do that is what is called backpropagation. So again, conceptually, what we're trying to do is to say, how do I bring loss down, and how do I allocate the reduction in loss that I desire to what the changes in each of these various components needs to be. So the change in W2, the change in B2, the change in L2, the change in L1, the change in W1, the change in B1, and therefore the change in input. And whenever I say change in, think of it as a gradient of that value. The gradient we just illustrate, at least initially in the notebook, as an attribute of the value. So change in output is the output gradient, so it's out.g. And we always calculate the gradient of something on the output with respect to the input. So what out.g is a gradient of the loss with respect to the output. That is the gradient that's going into this unit. What comes out of the unit, remember, is out. And what goes back into the unit is the change in output with respect to the change in the gradient of the output. The change in the loss with respect to the output, which is the gradient of the output or the out.g. Now, how do we calculate backdrop? There are three basic steps. You identify the intermediate functions or values from the forward prop and store them. So, for example, we store L1, we store L2, we store out. Those are needed because we will figure out that we'll be reusing those as we move backwards. The second thing we do is for each layer, such as the linear layer 2, linear layer 1, and the ReLU, we calculate the gradients just within the layer. So for example, let's take L2, and we'll work through this in detail in the notebook, worrying about the shapes and so on. Here, I'm just going to kind of, again, wordily and with conceptually explain with a lot of words. Then we'll actually go to the notebook and run it and look at it in a mathematical and shape-oriented manner. So in this case, the first step is identify all the forward. When we go through this network in the forward direction, we just store the values and the functions that we've calculated from what is called the forward prop. That's we are just going from the input towards the loss. Second thing we do is compute the loss of every block. So what does that mean? That means computing the gradient of, let's focus on this particular unit, that is the linear 2. So linear 2, remember, has an input, which is L2. And its output is out. So if you're just focusing on this block, then the gradients of the output with respect to B2 is just out, the differential of output with respect to B2. The gradient of the output with respect to W2, that's what is the missing thing here. And the gradient of output with respect to its input, which would be L2. So those are the three gradients when we compute this second step, which is computing local to this layer, the gradients. Now we'll worry about the shapes of these because the shapes do matter, right? Because we are doing matrix multiplication, and when we are computing the gradients and stuff, then what we do in order to multiply values, which are vectors and matrices, will matter. And then this third step is the critical step where the chain rule comes into play. In all, what we have computed, or what I've kind of wordily talked about, is just computing the gradients of this block, which is the out with respect to B2, out with respect to W2, and out with respect to L2. But in order to remember, what we are trying to do is allocate the difference in loss throughout the various values that are there in the network. In order to do that properly, and this is where the chain rule, that is the rule of differentiation that applies when we compose functions, comes into play, and we'll look at that mathematically in a little bit more detail in the subsequent couple of slides. What we have to do is multiply the incoming gradient or the incoming differentiated output from a prior unit in a downstream case, and use that to multiply for every gradient that we have computed within the block. So what that means, and we'll again look at it in greater detail, is remember that the gradient of the loss with respect to output is the gradient that's coming in, the first back arrow. Therefore, I've indicated that with out.g. So the gradient was computed within this, that is in the third step, we use the upstream gradient. The upstream gradient for this block is out.g. The upstream gradient for the ReLU block is its output's gradient, which is, remember, its output is L2, so L2.g. So similarly, I just wanted, instead of just me talking nonstop for 2 hours, what would be the gradient value of the upstream block here? Can somebody mention that? Anyone? What's the question mark value here? Anyone awake? Anyone? What is the upstream gradient coming into the first linear block? Sorry, I'm going to pick Mayank or Mehul or anyone. Anything I'm saying making sense, or? Questions? Thank you. Still there? Andrea, Emily, anybody have any thoughts on what the upstream gradient coming into the first linear block would be?
I'm here.
Go ahead, Emily.
I don't think I have an answer. I understand that it's well, I think I understand it's a composite of the differentials going back through the network, but I don't.
Okay, the simplest way to think of it is, remember that the output of, we have the equations, and I had the equation on top listed out, right, for the very purpose. So think of it as, what's the output coming out of the second linear layer? It's out, right? That's the reason why out.g, which is the gradient of the loss with respect to output, is the upstream gradient coming into the second linear block, into this block. Okay, that's out.g, is the gradient coming into this block. So you can see that in every instance, it is the gradient of the downstream block with respect to its input. That means the output coming out from here and the gradient of loss with respect to its input is the upstream gradient coming into this block. So let's do the same with this block. What is the output of the ReLU block? Well, the output of the ReLU block is L2. So L2, and there was it, I kind of deliberately didn't label these because I wanted people to think through it, and I would in fact encourage you to take this diagram and kind of label the output. So the output of the second linear block is L2. Is out. So that's why the upstream gradient coming in here is the gradient of the loss with respect to out. That's why I've indicated the reverse arrow, and the upstream gradient is out.g. the output of the ReLU block, you can see here is L2. So the gradient of the upstream gradient coming into the ReLU block is therefore L2.g. That is, it's the gradient of everything coming up to this point taken with respect to its input, which is L2, because this is this arrow at the bottom is the output of ReLU going into the second linear block, which is L2, right? That's the input, the second linear block L2, right? So this is L2. So when you're considering the output gradient, or I should say the upstream gradient coming into the ReLU, then it's L2.g. By a similar argument, what's the output of the linear block here? It's A1. So what's the gradient that will be coming into it, or the upstream gradient? It will be L1.g. That L1.g should multiply the gradient of the internal gradient that we're computing here. That will then be used to determine B1.g, W1.g, and input.g. Again, this is conceptual, but it's important to, I think, write these things out before you go to the next notebook or the next part of our notebook and kind of start working through the details of it in the notebook. Because unless you understand conceptually, it will just be a a kind of mechanical, mathematical manipulation, unless you understand the concept of the 3 steps that are used in order to compute the backdrop. In every instance, identify the values going forward. This is more so you store them, so it's easier to compute. This is more as a computational shortcut or caching. This is important to do. We calculate in every case the differentiation of the output with respect to the block's inputs, which is the weights, the biases, and the input coming in. And in every instance, we take the upstream gradient and multiply that to the block's internal gradients that we have computed. That is its own output with respect to its weights, bias, and input. But we multiply through the chain rule, and we say, this is how I want you to distribute the upstream loss among the inputs that this block is getting. And we continue to do this process to every block in the chain. That's how we eventually arrive at how best to distribute the loss or the reduction in loss across all of the parameters of the network. And what that does is it helps the network get better at tweaking the parameters such that the loss comes down. And when the loss comes down, our network's ability to predict the desired value goes up. That's how backpropagation helps the network learn. Quote unquote learn basically means tweaking our parameters and values so it gets better at predicting the function that we want it to predict. Right? So now, let's work through a simple chain rule example, and then we'll go switch through the notebook and work through the actual neural network and figure out in terms of the code how all this works. But let's start with a simple chain rule example. So in a simple chain rule, what we're trying to illustrate is, using a very simple example, what we mean by composition of functions and how the basics of a chain rule come into play. So let's say a simple y is a function of x function, but instead of x, let's say we use x squared. So y is 3x squared plus 9. But x squared is not x. X squared is some function of x, right? So we replace x squared by u, and we say y is 3u plus 9. Okay, and obviously the simplest of the differentiation rule that you need to recall is d or a differentiation of a to the power of b differentiated with respect to a is b a to the power of b minus 1. So using this generic definition of differentiation of a to the power of b, we use it to say d, if we were to differentiate x squared with respect to x, the answer is 2x. There are a bunch of rules like that. It's very simple. You can refer to Khan Academy for understanding kind of the basics if you have gotten differentiation. And there are very complex rules. You can look it up at any time. But let's say we continue with this differentiation problem of y is 3x squared plus 9. And what we want to differentiate or what we want to find out is dy by dx. So what we do is first we rewrite it as y is 3u plus 9. And then we write u is x squared. Now, how do we get back to dy by dx? The way we do that is we first, again, this is a very trivial example of composition of function, right? Y as a function of u is a function of x. So dy by dx is our goal. We first compute dy by du. When we do that, again, with simple rules of differentiation, this 3 times u to the power of 0. So it's u to the power of 1, I'm sorry. And so using this, we come to u to the power of 0 here, which is 1. So 3, arrive at dy by du is 3. Then we also compute du by dx, which according to this equation is 2x. To compute dy by dx, what we need to do is multiply dy by du and du by dx. So when we do that, then we say dy by du is 3, du by dx is 2x. We multiply those two values, 3 times 2x, 6x. So dy by dx for this equation is dy by du, x squared replaced by u, du by dx, therefore d by dx squared by dx, which is 2x, dy by du, which is 3. This is the chain rule. Now, there are more, evolved explanations of this. I've just taken one explanation that one of the students provided in the chat for the discussion. You can go back and look at that in detail. But basically, this is the intuition of composing linear functions and why we multiply the slopes of linear functions. So think of two linear functions. F of x is mx plus c. So basically, what we are doing here is multiplying, so scaling by m. So we scale the input by m and shift it by c. That's essentially what we do when we say y is mx plus c. We scale by m, shift by c, right? And then another equation, g of x, is nx plus d. So we scale by n, shift by d. So now if you want to compute the derivative of this composite function of x, you can kind of intuitively understand that if you have scaled by m and shifted by c and scaled by n and shifted by d, what we ought to do when we are trying to find the answer of how do we change x, which is a composition of these two functions, is intuitively it seems the right thing to do would be scale by n, which means that the thing we need to multiply it by is both n, or I should say the answer would involve multiplication of the two scaling factors. Therefore, n times n. So this is an intuition of why in the chain rule we kind of multiply m and n, if you will, assuming the functions are linear. But then the question arises, wait a minute, you are giving me this explanation, but you're kind of assuming it's linear. But what if it isn't linear? Well, then this is where the differential calculus comes into play. What we then assume is that the function is linear around a point. This is where the infinitesimals come into play, around small changes of a point of interest that we have. So the approximately linear around each point arguments that comes into play. So if you want to compute g of f of x, which is a composition of two functions, g and f, at x is x0, we can behave as if the function f of x is the tangent of x at x at 0, and g of u is the tangent of g at f of x 0. And if we do that, then we are back to the argument that we had originally, which is it's just a matter of multiplying the two slopes. Therefore, a matter of multiplying m. So what we argued with great detail in the linear case, once we move into differential calculus and use that concept, becomes true for any curve, right? Again, not a mathematically strict, but an intuitively better understanding. And then I'm not going to go through this. You can look at it in, I'll post a link to the slides later, but essentially this is just another working through of the math, pushing through it to indicate that dy by du is nothing more than, dy by dx is nothing more than dy by du multiplied by du by dx. So all these various explanations are just trying to tell us that when we go back through the neural network, as we want to do in order to determine how do we distribute the change in loss across all of the input parameters that we have, such as the weights and biases of each of the linear networks, then the way we do that is to take the differential, upstream differential coming into the unit, compute the differentials of the unit, multiply the upstream differential to the input differential, and keep going backwards through the network. Okay? That's what essentially all the math resolves itself to. Now, there's a lot more complexity to it than what I'm trying to say here. And if you're interested in the complexity and working through that and really getting a good grasp of it, there are a few pointers that I'll point you to. One of them is this particular write-up, an excellent write-up by Terence Parr and Jeremy Howard, the matrix calculus that you need for deep learning. It really gets you understanding differentiation with respect not just to scalars, which is what we have mostly worked through if you've done it in high school and not calculus, multivariable calculus through college. You learn what you need to from the write-up here. Secondarily, and a couple of the guys, I think Nehal was there, we also had a couple of lectures that we went through as part of the TWIML group itself, and I'll post the links to it, where we went through reading the write-up that I just talked about in great detail and discussing the various shapes that result and so on. And in addition, one of the best lectures that gives you problems of this kind to work through so you get a real understanding of how the shapes modify, what are the details you need to do, how does the distribution of the upstream gradient happen when the network is connected in various ways, is this lecture from the Stanford NLP course, and how to work physically through equations, the various distributions of backprop and the mathematics of backprop. So I'll post the lectures or I'll post the links to these things if you're interested in more details of working through an understanding of grasping in gory detail the backprop algorithm. But with all that said, let's push through the notebook and understand it now that we have hopefully some conceptual understanding how those concepts translate into math and code. Here I've already explained why MSU is not a suitable loss function. Later in the course, we'll kind of get hopefully through the rest of the lecture and get to understand a better loss function. But let's kind of see the shapes. Now, here is where the reality of working through math and shapes come into play. Let's say the result, as I mentioned before, of pushing through the network is a 10,000 by 1 output, right, of X valid pushing through the network, we result in the resultant output we get is 10,000 by 1. The Y valid is a single integer of, right, for 10,000 values of integers. So that has a shape of 10,000. Now, if we were to just try to calculate the difference by writing res minus Y valid, what do you think the shape of the output would be? Well, it kind of is unfortunately answered for us. If we just did this, it'll be 10,000 by 10,000. Why? Well, let's look at the shapes here. The shapes are mentioned here, and remember how broadcasting rules work. The broadcasting starts from the last shape. So the last shape is 1 here for the result, and it's 10,000 for the Y valid. So what does it do? It broadcasts this 10,000 across this unit axis here, and therefore the result is 10,000 by 10,000. Is that what we want? No, we actually want just the 10,000 values that the output of our network has predicted to be subtracted from the 10,000 values of our Y valid. But in order to do that, we will need to make sure that these shapes match for that subtraction. So in order to match that is where we need to get this shape of the Y valid to match that of the result, right? That can be done in 2 ways. We either squeeze the result shape, and whenever we say squeeze in NumPy and PyTorch and stuff, we get rid of all unit axis vectors in the shape. So 10,000 by 1 squeezed results 0 dot shape. We can either do that by saying result all the rows and the 0th column, which will make it 10,000, or we can squeeze the result. Either way, we get to the desired shape for the result, which is we get rid of this 1. The other thing obviously we can do is, add 1 to the shape of the valid, but that might result in other problems that we don't want downstream. So here we just kind of squeeze the result, and then we get the shapes, and then we subtract. So this is a very simple example of how, because of the rules of broadcasting and because of how the various shapes structure as we go through the network, it's important to not just blindly apply what we know we are trying to do, but to check the shapes at every step as we go through the notebook. So if we run that, get the shape as we want, we squeeze it, then we subtract it. So we now have the difference that we seek, which will be a component of the loss. Right? And he's here just kind of converting the train and the valid to floats. And then predicts is just putting the train model, right? So far we've been dealing with valid, we just switches it to train. So getting the predictions, and the predictions as we see are 50,000 by 1. Now the MSE is just, remember the subtraction has to be done in the proper manner. So MSE is output : 0. Essentially you could have done output dot squeeze minus the target powered twice or to the power of 2, and then take the mean. That's the definition of our MSE. And then we take the MSE of our predictions, 50,000 single values predicted, and the actual values of Y tree. Okay. And the MSE scalar value that we get is 4,308. I'm going to skip this. He just kind of says, hey, symbolic Python helps you kind of conduct differentiation by specifying what it is and so on and so forth. But here's the relevant portion, and I would very strongly encourage you to print out a particular box diagram that I showed and map the equations that he puts down here and write it down on that slide and see how they map. So before we kind of get into the linear grad, let's look at what forward and backward is and how we can do that. Right. So now I need to obviously run this in sequence because it won't, but let's kind of understand forward and backward. So forward, we just go through the network, stepping through the network in the forward direction as I showed below. So L1 is a linear of input W1, B1, L2 is ReLU, out is linear. Diff is just an intermediate term he has introduced of out squeezed, if you will, and subtracted from target. Remember, this squeezing is necessary, otherwise we get bent out of shape, so to speak. And then loss is the diff times power 2 by me. And now begins the backward pass. For backward pass, the first thing he says is, let's just, for simplicity, store the gradient that we want as an attribute of the value that we are computing it for. So if we are computing the gradient of the loss with respect to output, then we store it in output gradient or out.g. So store the gradients of each layer in an attribute of the layer. So out as an attribute out.g, which stores its gradient with respect to diff. Now, I think this is what I was encouraging you to do. At least I tend to do this myself, is write out the explanation so that when I come back to the notebook later, I have a clear explanation of what it is that's happening in the cell, right? Now, below is the gradient of the MSE loss with respect to output of our neural network, right? And here, the output of our L2 layer is called out. So out.g is 2 times the difference. Now we need to do this in order to get it into appropriate shape, and then divided by the input.shape 0. So this is just in order to get the mean. And that's what is put in the out.g. And this exactly corresponds to this out.g that I have here. So I'd encourage you to kind of look at this diagram, fill out the details, work through the shapes corresponding to what happens in the notebook. Then this linear grad is, because we use the gradient of a linear network twice. Remember, we have to do that for the L2, and we also have to do it for L1. So because of that, we code the details of taking the linear grad in a separate kind of function. Now let's just look at, before we see the usage of linear grad, or we can do this first and then go back to the details. All we're doing is we're saying, now let's take the gradient of the linear layer. For the first time we do this, which is for the second linear layer in a network, the output of that second linear layer is out. The input is L2, and the weights and biases are W2 and B2 respectively. So we say linear grad, and this is a function we'll get into in a minute, but we say linear grad, L2 out, W2, B2. So what happens as a result of this? Well, what happens as a result of this is we have computed the gradient of the resultant values, or we have computed the gradient of the second linear layer. And as a result, we have computed 3 values, L2.grad, W2.grad, and B2.grad. L2.grad, L2 is the input, W2 is the weight, and B2 is the bias. So remember that what we wanted when we came in is we will obviously use the gradient of the output and then compute that box's internal gradients. Okay, so that's what we've done by this function. We keep going back. The next is to compute the gradient of, go ahead, Mike.
Yeah, here,
a question?
dot G and dot grad are 2 different patterns of referring to the same variable, or?
There is no dot grad at this point. It's just, right now, we're just storing the gradient in attributes called dot G. What he will eventually point out is this is something that he has done in order to illustrate or in order to say we can do what PyTorch does ourselves. But once he has illustrated that we can, with our own code, do what PyTorch does, he'll back off and start using the PyTorch variants. In PyTorch, the gradients are stored in a variable's .grad attribute, not in .g. But in order to not confuse us, we are storing the gradients that are computed in an attribute that he creates called .g. Does it make sense?
Yes. So .g here refers to the attribute that has the variables of the forward or the backward pass.
No, .g does only the .g attribute of a variable is the gradient of that variable.
Okay.
Now, what is the gradient of the variable? You have to look at it in the context of the network. So out.g is, that's why the diagram that I have in my slides is important. Out.g is actually the gradient of the loss with respect to the input coming into the loss module, which is out. Therefore, out.g stores the gradient of the loss with respect to output. Similarly, L2.g will store the gradient of the out with respect to L2, and that's L2.g. And the gradient of W2 and B2 will be stored in W2.g and B2.g. Okay, so let's now get into the code for linear grad, which will explain it even better. The definition of a linear grad. Now, remember that this is a function which computes the gradient of what? Of a linear unit. The linear unit has an input, it has an output, has a weight, has a bias. For the second linear layer in our network, this input coming into the second layer is L2. Go back and check what it is in our log diagram or in this equation, and you'll see that this, and I didn't mark it here, but you can write it. I left it as an exercise because it's important to write this down and figure it out yourself. But this second bottom arrow is L2. Okay, so the second linear layer as an input of L2. What is its output? Is out. W2 is the weight, B2 is a bias. So remember this as we go through the equations here. Here, the INP, because he's building a generic value that he can reuse for the first layer. For the second layer, this input is L2. The out is itself called out. W is W2. B is B2. Now, this is where what we are trying to do in this function is calculate the essentially this backprop stuff, specifically this guy. Okay, and we'll obviously have to worry about or compute the local gradients and then how to combine it with the upstream gradient. So we are doing these two things, assuming we have access to this thing. Why do I say that? Remember, INP is L2, out is out, W is W2, B is B2 for the second linear layer. What is the gradient of the output with respect to the input, which is stored in the input's gradient attribute? So that's input.g. And what it is, and this is where, again, to understand why he has written it as a matrix multiplication of output.g, and why is he transposing the weights, w.t. In order to grasp that, you'll need to understand how derivatives of scalars with respect to vectors and derivative of vectors with respect to vectors, how they show up, okay, or what shapes they have. Now, slight detour, that is what is explained, if you will, much better in the write-up that I pointed to earlier. These derivatives of vectors or matrices with respect to scalars, with respect to other matrices, those resultant values are called Jacobians. Okay, again, don't get terribly put off by the terminology. It's just something we call something. Okay, it's as simple as that. But what is more important to understand is if we differentiate a scalar with respect to a scalar, or a vector with respect to a scalar, or we differentiate a scalar with respect to a vector, or a vector with respect to a vector, what are the resultant shapes? That is very important to understand. Why? Because these things, these layouts, or these shapes is what actually ends up determining why, when we do the differentiation that he has written out, he just writes it out as input.g is out.g matrix multiplied with W transpose. But wait a minute, why the hell did we transpose W? Of course, the explanation for why we multiply by out.g is simple. As I told you, for any block, any linear layer or anything else, we take the incoming or upstream gradient, which is out.g, and we multiply that. That's the chain rule with what is the gradient we're trying to compute. Okay, but in order to understand how the shapes mark themselves, why do you take transpose? In what sequence do you arrange those in order to get the resultant shapes to line up? That is something, in order to understand that, you'll need to go through the matrix multiplication, or at least work through the Stanford lecture and a few examples from that to really grasp how to do that correctly. And short of doing it yourself, no amount of explanation actually, in my experience, gets you going, oh, now I understand what's happening. You really need to push through at least a few examples to understand how the math and the shapes work out. And then you can kind of intuitively begin to trust and apply them going forward. Now, again, this is just a simple version of a scalar differentiated with respect to scalar, a vector with respect to a scalar, and a scalar with respect to a vector, and a vector with respect to a vector, right? And these are explained in great detail in the write-up that I refer to here and that I'll provide you a link for. Now, interestingly, we are not done here, because this is just simply scalar functions with respect to scalars, vector functions with respect to scalar or vector. But remember, we are not just doing single functions. We are actually doing composition of functions. So that makes it even more challenging. And this is the eventual set of rules that you'll be applying in order to get to the shapes that he uses in the notebook, which is the vector chain rule components of the Jacobian. So here, what we have is a composition of functions. So function f of g of x is del f by del g, and then del g by del x. This is just chain rule. But now we have to think about the following. Each of g of x and f of g could be a scalar or a vector. X can be a scalar or a vector. G of x can be a scalar or a vector. So that's what this thing represents, a scalar, a vector. But when we differentiate a scalar with respect to a scalar, or we can differentiate a scalar with respect to a vector. Of course, we differentiate a vector with respect to a vector. And then we say, okay, this is all G on the top here. But what about f of G? Oh, well, we now have to again consider that f of G could be a scalar or a vector. And when we push through all of these are the resultant steps or shapes that you get. Now, in every instance, and again, as we go through the higher levels, as we see later on, even in this discussion, we'll end up with the computer doing most of the work for us. But it's important to understand, at least at a minimum, the shapes that result, because otherwise we won't be able to compute or work fluidly or fluently with the resultant values. Okay, that's back to the equation here. So now what we're trying to do here, remember, is the input coming in is L2, the out is out, W2, B2. So when we compute the gradient of what we aim to compute is this block's gradient, the gradient of the input, right? And the input's gradient, remember input in this case is L2. So L2.g will be the out.g matrix multiplied. As I said, or keep repeating, why the shapes are or why we matrix multiply it with a transpose of W is something that you'll have to work through the shape details in order to understand. But what conceptually this clearly points out is you take the incoming gradient or the upstream gradient coming into this linear L2 block and matrix multiply it with the transposition of the weight to calculate the gradient of the input. Remember, here input is L2. So what you have calculated by this single line of code is L2.g. Then we also need to calculate W2.g. What W2.g turns out to be is, and again, you'll need to work through the shapes, is unsqueeze the input in order to match the shape of out.g, again, unsqueeze that in the first level. So these two shapes match. And as he talks about, I highly encourage you to, again, either print out the shapes of input and the shape of output before you squeeze, right? And then unsqueeze as it's stated here and see how the shapes change and how it results. Basically, when you do that, then you do this equation. What you're again doing is taking the upstream gradient, out.g, although you're morphing the shape, multiplying it by the input, and then adding the sum. And when you see this kind of multiplying two matrices followed by a sum, essentially it's a matrix multiplication. It's just a matrix multiplication that's stated here. It's input transposed, matrix multiplied with out.g. That's what this complicated equation actually says. So now we have calculated W2.g, and B2.g is just basically output.g and summed along the rows. That is, all of the 50,000 values contribute to the bias, right? Now, what I have commented here is all of this is, these comments are with respect to L2, okay? And all this squeezing and stuff that he does here is in order to get these shapes to align to what we actually want it to be. And if the same equation is used for level 1 or linear layer 1, then remember the input coming into it will be L1. It's the output of the gradient that we take from the ReLU, right? So, sorry, that would be the output. And the input coming into it is X. And W is W1 and B is B1. And then you can work through, this would be the gradient with respect to input. This would be W1.g, this would be B1.g. Does that make sense, or any questions? A lot to get through. I think the best is spending a lot of time with the notebook, working through its various shapes and so on and so forth. Right. So I think I ran these two equations, these two cells. And so what we have done, as I mentioned, once we go through the Leningrad here, this particular line of code that I've highlighted, it essentially helps us to compute. We already have out.g. It helps us to compute L2.g, W2.g, B2.g. Then what we do is we compute L1.g. What is L1? Again, go back to the slide and we kind of figure out that in the ReLU, now I've already described the ReLU function, it clamps to 0, anything below 0, and anything above 0 is the same as x. Therefore, the derivative of it is whenever it's positive, it's the same as x, so it's 1, and whenever it's negative, it's 0. So basically, that's what this says. L1.g, that is the gradient of L1, is basically L1 greater than 0 float. And then remember that the upstream gradient coming into it is L2.g. So that's why we multiply the gradient of the ReLU, the internal gradient, and then we multiply it by the upstream gradient. Okay? And that's what my comment says. And then again, for the linear grad, what is the upstream gradient? The first linear layer, it is L1.g that we have just computed, because L1 is its output, right? So the upstream gradient is L1.g. So then that's what is something that we have here already. When we give it L1, we already have its attribute L1.g. And we compute input.g, w1.g, and b1.g using this cell or this set of equations. Okay, so that's what have we done by forward and backward? Basically, what we've done is what I spent all this time explaining. We have kind of decided, or through math and through chain rule, figured out how do we distribute a change in loss to the various parameters that we have. That is to the W2s and the B2s, to the W1s and the B1s, through taking the differentiation of every block by itself and then multiplying the upstream gradient to, or multiplying by the upstream gradient, the internal gradients we compute. And the reason to do that is so that we can appropriately allocate all the changes to the parameters that we have chosen. When we do this, then we have figured out a way to improve our network as the loss reduces. So as the loss reduces, we'll become smarter at allocating the changes, or we can talk about it in the other way. Then we will be smart at making the changes in a direction such that it helps reduce the loss. But the way we do that is by going backward through the network and allocating the changes to be made such that the network improves so that our loss goes down. You can think of it in either way. Right? So now if we run forward and backward, which is all these equations here, through X train, which is our input, and through Y and Y train, which is our eventual output, then what would have resulted from this? It takes a while. Why? Because as it goes forward, it computes all the forward values. It stores all the forward values, and then it goes back and computes the gradient W2.g, B2.g, L2.g, L1.g, W1.g, B1.g, right? And the beauty of it is all this code is code we have written. We have not touched PyTorch yet. So now he just says, wow, I'm just going to do a cheat and use a simple way to check the gradients you have computed, because PyTorch does all of this, obviously. And we are going to compare the gradients we have computed with the ones that PyTorch computes. So this thing just says, we're just going to, this cell just, says that the gradients are all these values, and I'm just going to map the get gradient function and clone them. I don't want to change, so I'm going to copy them and then run the map function to the checks, which checks are all these values. So it just computes the gradients, right, to store them, creates copies so we don't change the originals. And he says make grad, clone, and this request grad true just says that for a variable in PyTorch, if we say required grad equal 2, that means you are allowing its gradient to get computed. So we do the PyTorch gradients we compute by saying map make grad. So here, this cell actually uses PyTorch to compute the gradient. The forward just says, I am giving it the input, giving you the target, and I'm going to use these values. It's just a re-specification with slightly different values, if you will. So PyTorch doesn't, so that we keep the variables separated, and then we calculate the loss, and we say, wait, the PT grads are the PyTorch computed values. The grads are our own computation. Let's just, for each one of them, check that they are identical. So basically what we have done through all this discussion and stuff is try to understand or grasp what happens as we train a neural network and what's the concept of back propagation. How do we attribute the changes or the desired reduction in loss and distribute it across the various parameters we have the ability to change? For looking at it in a forward direction, how do we tweak the weights and biases of our network in order to get the network to produce a lower loss, thereby get better at predicting the digit that we are seeking? The rest of this is just basically refactoring the model. So, you can have a dunder call attribute to any class in Python, which basically says you can provide a value such as the name to the class, an instance of the class, and that will then print hello Sam. So you can kind of go through that and understand what a dunder call does. So what we are now doing is recoding the classes as using the dunder call function. And the reason for it is we are building the ability to store attributes as we move forward, so that when we come back, we can use those values. When I say when we come back, what I mean is so that as we compute the gradients, we can use stored values. So by using classes, we store them, and then we compute through methods the forward values, return them, and we also have a backward function which helps us compute the gradients. Okay, so ReLU is the simplest, so we start with that. So given an input, we just store it. We know the output is just input clamped to the minimum to be 0, so no negative values, and then we return self.out. So this is the basic function of a ReLU. But to that, we add a backward method which helps calculate the gradient. We store it in the input gradient attribute. So self.input is the input coming into the ReLU, and we store the gradient in input self.input.gradient. And what it is exactly the same code, except that we also multiply it by, as we've seen when we did the detailed work up above, by the upstream gradient that's coming to us, right? And we already know that the self.out is the output that we have stored. And its .g attribute will be the upstream gradient that we have computed and will be given as an input to us, right? So when you can go back and look at this equations when we do the forward and the backward, and this, sorry, not that one. This one is essentially what we have done here. So you can go back and forth in the notebook and see what simplification he is incorporating here. Okay, let's keep moving. Similarly, we write the linear layers as a class. We have the weight and bias, the input. The output is a linear of input and then the weight and the bias. Return the output. Here's the additional method we have introduced, backward. So what happens? Remember, you go back and check self.input is self.out.g at self.w.transpose. Now self.out.g, this is the output of this layer. Self.out.g is the upstream gradient that's coming into you. stored in the attribute of self.out. So you can go up here and check that that's essentially what we have used. Sorry, let me pick one. So let's say self dot, actually this is an easy one, just to compare self dot input dot g is self dot out dot g matrix multiplied by self dot w dot transpose, right? And you compare that to this guy, you can see other than the self dot, it's exactly the same. Right. So you're just simplifying the model by rewriting the layers as classes in order to be able to store the output, and then also have a backward method which allows us to compute the backpropagated derivatives of the block. Okay, so every block. So for example, a linear block will have its gradient. Remember, the linear block has three inputs, or three inputs, right? One is the input, the other one is W1, the third one is depending on the layer, it's W1 or W2, but generically speaking, it has a weight, it has a bias, and it has an input. So we need to calculate the input gradient, the weight gradient, and the bias gradient. In each case, we also need to multiply each of these gradients by the upstream gradient. The upstream gradient coming into us is the gradient of the output. It's stored in the outputs .g parameter. So basically, we kind of see that in every instance, we use self.out.g to multiply. Now, where it multiplies, by that I mean on which side and in what matrix shape, those factors are determined by what I quickly ran through of, what happens when you take a derivative of a matrix with respect to a matrix, and what happens as you compose the functions, and so on and so forth. But for a simple two-layer linear network, it's very easy to work through the shapes and convince yourself that these are the correct equations. But I would highly encourage you to go through it yourself in order to really grasp the complexity and at the same time the simplicity of how it eventually all these are based or built out of few basic principles. And then of course the MSE, again, this is something exactly the same, except that we have to kind of code it appropriately to get the right shape. Okay, so after having gone through all that, one other variation, if you have worked through any other framework like FastAI or even any other typical, even PyTorch itself, the observation it makes is that often you find the case that the loss function is not built into the model, but apparently in Hugging Face, the loss function is integrated into the model. Now, there are some reasons why. In typical cases, you want the loss function to be separate because, as I mentioned, it's often the case that you want to change the loss function but keep the network the same. And if it's part of the network, then you have to kind of go and stitch inside of a module. But if you keep the loss function separate from the model, then you can change the loss function a whole lot easier without changing the model. But that's a detail that's important only to know, so that if you're working with Hugging Face data sets or models, then you know how they work and where to modify them. That's something that's mentioned here, and you can see that here is included in the model the loss function as well. That's typically not the case in FastAI or in PyTorch. But let's push through this because we'll be using the example of Hugging Face data sets quite often. So the model just says I'm just using two linear layers. The layers are linear W1, B1. The value linear. So essentially, this is a list of layers that we have created a two-layer linear network. Linear 1, W1, B1 being parameters, value, linear 2, W2, B2 being parameters, and then the output of that goes to an MSE. Here, in this initialization, we're just defining the functions. In the call, what we do is for each layer, that is for each of the layer in our list of layers, make X by passing or make the output the function call of X. So what do we do when we write this line of code? What we are saying is take X, pass it to linear, W1 linear, first linear layer, the output that comes out, pass that to ReLU, the output that comes out, pass it to linear, the output that comes out of here, pass it through the loss and give it the target. Because remember that the MSE requires both the loss, the MSE loss requires both the output of our two-layer neural network and the actual target that we know we have. This is the integer that we are seeking to predict, right? The additional method that we are describing is a backward method where we start with the loss and we compute the backward of it. And then for every one of these layers, we compute the backpropagate, right, using the backward method. But there's an important thing to keep in mind. We want to go backward through these layers, right? Therefore, for layers in reversed self-dot layers. Why do we reverse it? Because when we are going back, we want to kind of start here and go backward. When we are going forward here, we want it to go this direction. That is, the output of linear is the input is sent to linear, the output of that is sent to ReLU, the output of that is sent here. When we do backpropagation, we start with MSE, compute the loss, and then we go backwards through these layers. Okay, so that's what this particular code does. So we then say model is just a function, and we give it the parameters that we seek, W1, B1, W2, B2. We compute the loss, model of X train and Y train. Then we say model.backward to kind of backpropagate, execute our backpropagation, and then we test that the variables that we have computed are all close to the values that PyTorch computes. Okay, so again, this is yet again just a simplification of the module that we have coded so far. Let's define a module class. It's a template class. The template class just says when I call it, I'm going to take the argument, store it, compute the out, and compute the output based on a forward method that I'll describe, and I'll use the parameters that are sent to me, and I'll return the output. If you see, that's essentially the structure of every single function that we have described. Compare this code or the linear code or the MSE code to the template that he has described here, and you'll see that the template kind of pretty much covers it, right? We're almost at the end of our session of 2 hours. I thought I'd be much further along, but I think, it's the time we spend is important to understand the details. We will start at the module.forward and take us through the remainder of this lecture, and I'll try to see how much of the next lecture also we'll be able to cover next week. Any questions anybody has that they'd like me to answer? We went through a lot of math and shift twisting and storing variables and switching between slides and notebook. I would highly encourage you to play with the notebook and add the comments yourself, like I've done in my instance of the notebook. Work through and try to listen to, or at least read through. Have any questions from the Terence Parr, Jeremy Howard paper? Feel free to ask those on Slack, and I'll try my best to answer. But these are the fundamentals of backpropagation and automatic differentiation that helps us build all these neural networks. Any questions, comments, anyone? If not, thanks everybody for joining. It's 10. Thanks for sticking with us through the 2 hours, and we'll see you all next week.
Thank you very much. Very, very interesting material.
Thank you. See you all next week. Bye.
Thanks everyone. Take care.